Right there guys, it's Mr. Pope here from Winton Grammar School for Boys, and today we're going to be talking about the hypothesis testing, and we're going to introduce it by the means of the binomial distribution. So, first of all, let's remind ourselves what the binomial distribution is. So we would say a random variable x, which by the way is discrete, i.e. has packaged outcomes. So for example 1, 2, 3 and so on. You can't have a spectrum, a continuous spectrum of results. We'd say that this random variable is binomially distributed, with n being the number of trials and p being the probability of success. Now these are the only two parameters. So this is the number of trials and this is the probability of success. So if I was to draw, say, something like let x1 be binomially distributed by n being, let's say, 2 and probability of success being 0.5, where this would correspond to coin flips, then what's going on? Well, we're either going to get heads and a heads, or heads and a tails, or a tails and a heads, or a tails and tails. So let x be the number of heads we get, then either we're going to get 2 heads 1/4 of the time, or we're going to get 1 head 1/2 of the time, or 2 tails 1/4 of the time. So if I was to put this as little x as being my score, and this is a probability, then 0, 1, 2 would look like this. Maybe I should make that approximately double, like so, where that's 1/2, this is 1/4. Okay, now the diagram that I've shown here, the probability distribution graph, is going to come important. Well, it's going to be important when we start looking at hypothesis testing. Okay, so what is hypothesis testing? Well, hypothesis testing is all about using a distribution, whether it's perceived or experimental data, to check whether a hypothesis is true or not. So, what is a hypothesis? A hypothesis is just a testable statement. Okay, it's just a statement that we can test against. We can say whether it's true or false, right or wrong, yes or no, and so on. So here are the steps. Step 1 is we choose our hypotheses. And generally speaking, we have H0, which is called the null hypothesis, and H1 is the alternate hypothesis. Now there's examples where that's not necessarily the case, but for most of the distributions that we're going to be testing against for at least the immediate future, it's just going to be H0 and H1. So what is H0? Well, the null hypothesis is usually the underlying or assumed position on something. And the alternate hypothesis is the accusation or the belief that something is different, usually. Now, essentially, hypotheses you can define however you want to. So, for example, I might say, well, I reckon that this coin... Actually, no, let's do the whole thing and I'll do an example. So the first thing is you write your hypotheses. The next thing you're going to be doing is you're going to be choosing the distribution that best fits. Okay, now at the moment we've only seen the binomial distribution. Okay, but there's so many others. There's the normal distribution, the negative binomial, Poisson, geometric. There's so many. There's so many. And we're going to be covering lots over the coming weeks. But at the moment, we're just going to be looking at binomial distribution questions. What else can we do? Well, once we've chosen the distribution, we're now going to find one of the following, or both. We can either find a test statistic or critical values. Okay, so lots of different things we're talking about here. Now, to get an idea of a test statistic, I'm going to do the following. Well, to be fair, the test, you don't really find the test. The critical values or the region. Right, the test statistic is essentially the value from the data. We'll talk about that in a second. And the critical values of the region is where any test statistic in that region will mean that H1 is true. So let's suppose, well, we need to back up a little bit. Before we can find the critical regions and so on, we really need to have our significance level. And typically that's around 5%, but it could be 1%, it could be 100%, or not 100%, lol, it could be 10%, it could be lots of different values. Now, when we start talking about the power and size of the test, you'll realise why there's a trade-off between having a high level of significance and lowering the efficacy of the test, and similarly having a low level of significance and just generally messing things up. When you mess around with the significance level, you introduce all types of things, literally type 1 and type 2 errors potentially. And we will be talking about that at some point, probably in the next 2 or 3 weeks. I can't remember the schedule. But the significance level is pretty important. And then once we've done the test, we state our conclusion. Okay, so yeah, pretty much these steps in order are what we're talking about when it comes to hypothesis test. So let's have an example of what's going on here. Let's suppose, fine, let's take an easy example. Let's suppose I've got a coin. There it is, there's my coin. And here's the head, kind of, with the crown. Right, there's my coin, very bad coin. And this coin is flipped 20 times. And I get a heads 15 times. Now, can I conclude, is that enough? What I'm trying to say is that enough evidence to suggest that this coin isn't fair anymore at the 5% significance level? Okay, so let's suppose I flip a coin 20 times, it lands on heads 15 times, and is this enough evidence to suggest that this coin isn't fair anymore at the 5% significance level? Okay, so when something like this comes up, then immediately in your mind you should be thinking, okay, they've talked about a significance level, we're wanting to look at evidence, we want to test a hypothesis, is the coin fair or not? So choose the hypothesis. So what would I do? So my null hypothesis is that the probability of the coin success being fair, the probability should be 0.5. It should be 50% of the time heads, 50% of the time tails. Now, if the coin isn't fair anymore, then the alternate hypothesis is P is not equal to 0.5. Now, it didn't specifically state whether the probability had increased or decreased. We just think that the coin's not fair anymore. So here, I've set up my hypotheses. Okay, in actual fact, I'll talk about what happens over here if we were to assume that if the null hypothesis is 0.5 and the alternate hypothesis is P is greater than 0.5, because it's a slightly different calculation. Okay, next up we're going to choose our distribution. Well, that would be fair, that would be the same in both cases. Well, clearly X is the number of heads, where X is distributed binomially by 20 trials, and the assumed position is that the probability of success is 0.5. So a binomial distribution seems to fit what's going on here. Next up, the significance level is given as 5%. So you usually see in textbooks that is alpha. Alpha is 5%. And now I want to find the test statistic. Well, the test statistic is 15. So we're checking 15. And now we need to calculate the critical values or the region. So, okay, now, if the coin has been flipped 20 times and the probability is 0.5, then what's going on is I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Potential outcomes, 21 potential outcomes, and all of these are going to form bars. So 10 and 11 are going to be the joint tallest, and because it's symmetric, you should see something like this popping out. Something like that. Maybe. I haven't drawn this super accurately. But the point is, if P is 0.5, then this should be symmetric about the middle. And also, if I was to take the midpoints of each of these bars and join them up, it should look like a symmetric curve looking like that. And to be honest, when you're just calculating critical regions, it's not particularly, if you're just drawing a sketch to aid you, you don't necessarily have to do this. And in actual fact, I'm not going to draw the bars in future things when talking about the distribution for the binomial, even though technically that was going on. If I was going to consider the case over here, I'd get ready. Okay, now here's the deal. The way I like to think of it is if the probability has changed from 0.5, then I want to consider the most freaky probabilities and the least freaky probabilities. And what the significance level does is if I'm checking between the lowest and the highest probabilities, then that 2.5, that 5% needs to be split in two so I can see the top 2.5% and the bottom 2.5%. So the question then becomes, where do I draw a line such that this region is 2.5% of the total and this region up here is 2.5% of the total? When I've got P is greater than 0.5, then I just want to draw a line so that the top region is 5%. If it was that I had P was less than 0.5, so for the less than ones, I would want to consider the bottom most freakiest of outcomes. Now the idea is that if I can prove that the test statistic, which is 15, is in these most extreme cases, then that means our original position can't be true. Our H0 cannot be true. And these outside bits, they are called the critical region. And this bit inside is the acceptance region. Another way of thinking about it is if it's inside the acceptance region, then you take H0 to be true. And if it's inside the critical region, the outside bits in this example, then you reject H0 and say there's enough evidence to suggest that H1 is true. Anyway, moving on. So the question is, how do we find the critical values? Where do we find these boundary points? And it's pretty simple. What we're going to do is we're going to use our calculator and go to statistics, and we're going to use the binomial CD function, which stands for cumulative distribution. Cumulative distribution. Now, on the Casio 991EXs, you press menu and then I believe it's 7. On the Casio CG50s, it's menu and then 2. And then because I've got a Casio CG50 right on me now, you would press dist, you press F5 for distribution, then F5 again for binomial. And what is beneficial with the CG50 calculator is you've actually got something called the INV B, the inverse binomial, which is incredibly useful here. So if I use that inverse binomial, I can set the area to find the bottom area. I set it equal to 0.025, which is 2.5%. I really hate motorbikes. Why can't they just drive normally? Anyway, so the area is 0.025. The num trial, so 0.025, the number trial is the number of trials. Well, that's clearly 20. That's part of our distribution. And our probability of success, P, was 0.5. I press that and it should say X equals inverse of 6. So that means, actually, this is a little bit wrong. I need to go up to and including X is less than or equal to 6 in order to get a region where this is 0.025. So any value that's less than or equal to 6 would fail our test. And then similarly, now, if I want to find the upper acceptance region, you've got to be a little bit careful. Because, think about it, if here is 2.5%, then everything from here to here is 100 minus 2.5%, which is 97.5%. So if I do the same thing, so area equals 0.975, n equals 20, and p equals 0.5, we will get an inverse binomial of 14. Now, let's think about this very carefully, because if I go to my CD function, my cumulative distribution, and I have the lower as 15, the upper as 20, number of trials 20, and that, I get so-and-so. Then if I put 14, yeah. Okay, so this 14 is where I need to draw the line. So actually I should have gone, so up to and including 14 is the 97.5%. So that means the critical region is X is greater than or equal to 15. Okay. So, here you go. So, any value that's less than or equal to 6 but greater than equal to 15 would seem to suggest that this is well, it's not fair. Let's go 0, 6. Ooh. Yeah. Let me just double check that. Right. Well, there's problems here because this is a discrete distribution. 2.5% isn't going to be exactly between two boundaries. It's going to be to the upper and lower of one, and it depends on the question which one you choose to do. So if I tweak this question so that you, so let's say, let's have it so that the significance level of both tails is less than or equal to 2.5%, then in that case, I think you'll find that the greater than or equal to 15 one is correct, because the probability that x is greater than or equal to 15 with the calculators is 0.02069, which is going to be smaller than or equal to 2.5. And if I was to do the probability x is greater than or equal to 14, that works out to be 0.05, so that's not good. And if I look at the other end, the probability that x is less than or equal to 6 is 0.057, but if I do the probability x is less than or equal to 5, that's 0.021. So in actual fact, the critical region by this definition up here, which usually is given in the question, is that the critical region is actually less than or equal to 5. So, since my critical region is less than or equal to 5, or x is greater than or equal to 15, and since the test statistic of 15 is in this upper one, then therefore there is enough evidence to reject null hypothesis and say the coin is no longer fair at the 5% significance level. Okay, if I was to go over to here, I want where the top 5% is. Well, if I do distribution binomial, inverse binomial, and now 0.95, so that's apparently here. Well, that's greater than or equal to 14, isn't it? Because if I try binomial CD and I want 14 up to 20, then the probability that x is greater than or equal to 14 is 0.0576. The probability that x is greater than or equal to 15 I just had, which is 0.02069. So because this one is nearer to it, I'll take that. So anything greater than or equal to 14 is in the H1 critical region, and below it is H0, the acceptance region. So I would do a very similar thing and say, since that 15 is above the critical value of 14, then it would fail the test and reject H0. If somebody said to you, given that, given these boundaries, what is the actual significance of the test? Well, that's quite easy. It's terrible. What you would do, the actual significance is where you just add up the probabilities they actually were. It's essentially saying you can't get 5% because you need to pick boundaries, i.e. values, not just partitions of them. So if you take the probabilities and add them together, so what's that in this case? It's going to be 0.04 1/6, something like that. If you add this thing and this thing together. Right, so maybe not particularly clear. You'll get it with a load of practices, and I'll probably just finish up just going through a couple of examples. But yeah, essentially what you're doing, the main flavour of it is you're choosing a hypothesis, you're choosing a distribution, and you're saying given a pair of hypotheses and a data value from an experiment, is the results from this experiment freaky enough to make you change your mind? Is it in the top significance level percent? So is it in the top 5%? Is it in the top 1%? And so on. See, now look what have happened if our significance level alpha was actually 1% and we changed it again. So if I'd have gone back and put it, say, like this, so exit, distribution binomial, inverse binomial, I want the area to be 0.99. So actually, the critical region would have been x is greater than or equal to 16 in this case over here. And for the one on the left, because you're splitting that 1% between two ways, then it's 0.995. So actually, that's going to have an inverse binomial of x is greater than or equal to 17, or x is less than or equal to 4. So in that case, at the 1% significance level, it would actually fail the test, and we'd say, well, actually the coin seems pretty fair. So notice how going from a 5% to a 1% could actually change the outcome. Another way of looking at it is you could say, well, because the significance level was 5%, you can say that I'm 95% sure that something's going on here. But then if you lower it to 1%, you could say, well, actually, I'm 99% sure something isn't going on here, and it seems pretty fair. Or another way of looking at it is if it fails the test and it's in this outside bit, you can be that much surer that it's weird. For example, if the test statistic was 18, then it would fail at the 1% level, and you'd say, yeah, I'm 99% sure something's not right here. There's a little bit of like intuition and feeling that something's not off here. And that's generally what I want to be building from this video. Anyway, let's go through a couple of examples. Calculating binomial cumulative distributions. I think I went through in a previous video. Let me check my summer plan. Yeah, it was the last video, discrete random variables including binomial distribution and combinatorials. So if you're unsure how to use a calculator, look back on there. But yeah, it's pretty much menu, then option 7 for statistics, and then follow it for binomial CD or binomial PD and so on. I'd probably say that the CG50 is probably more useful for this kind of thing because it has the inverse binomial function, whereas the Casio FX991EX series doesn't have that. So if you want to guess, if you want to know where certain percentage points lie on the cumulative distribution, you're going to have to use the list function and then list out a few things just by guessing what the distribution is like. And you can do that by thinking about how the distribution is. For example, if P is close to 0.5, if P is close to 0.5, then the distribution is fairly symmetric. That is terrible. If P is 0.5, the distribution is fairly symmetric. If P is less than 0.5, that means you'd expect the distribution to be positively skewed, i.e. you wouldn't get many successes. And if P was greater than 0.5, you'd expect it to be negatively skewed, i.e. you'd succeed most of the time. And so you can probably check, well, actually, you've got to go pretty high up for the extremes, and you have to go pretty high up for the lower extremes as well. And you can just use your common sense of where to pinpoint things down. Anyway, let's do a couple of questions. So, if you think you're getting the hang of it, pause the video. I'll go through it in a sec. Okay. Nazir is playing a game with two friends. The game is designed to be a game of chance, so the probability of Nazir winning each game is 1/3. Nazir and his friends play 15 times. Right, stop. That means we've got a distribution that's distributed binomially, where there's 15 tries, and the probability that Nazir wins is 1/3. Done. Find the probability that Nazir wins exactly 2 games. Okay, so it's the probability that x equals 2. So I'm going to use my PD function on the binomial bit. That's easy. So menu 7, then distribution binomial, PD function, variable. I want my x to be the number of successes, which is 2. My number trial is 15. My probability is 1/3. You can use the fractions button on here. And that apparently is 0.0599. So 5.99%. More than 5 games. So probability that x is greater than 5. Well, that's the probability of 1 minus the probability x is less than or equal to 5. Right? Think about it. Because winning more than 5 games is the complement to winning less than or equal to 5 games. So I'm going to use the CD function here. So distribution, binomial, CD function. Less than or equal to 5, so x is 5. With the Casio CG50, you can actually just do the upper and lower bounds. So greater than 5 means you want the lower bound to be 6 and the upper to be 15. And the num trial is 15, so p is 0.33. So you will get a value of 0.3816 here. Yeah, I'll take that. Okay, Nazir claims he has a method to help him win more than 1/3 of the games. To test this claim, the 3 of them played the game 32 times and Nazir won 16 of these games. Right, so now we've got a different distribution, let's call it Y, where there's actually 32 trials and the supposed probability is still assumed to be 1/3. So the null hypothesis is the probability is still 1/3, and the alternate hypothesis is Nazir thinks he's actually increased his odds of winning, so P is going to be greater than 1/3. Okay, now since P is 1/3, that means it's going to be a positive skew distribution. Now, I want to clarify, this would be what the probability distribution would look like if it was continuous. I know it's not continuous, it's just full of lots of rectangles and there's no actual curve. I'm just approximating those rectangular heights or the heights of each rectangle by a curve. Please do not take that seriously, always have that in the back of your mind. And I want to find at the 5% significance level, so where do I drop that bar down so that here is 5%. So using my Casio CG50, I'm going to do the inverse binomial. And I want the upper 5%, so I want the area to be 0.95, and num trial 15, and so on. So apparently, if I draw the bar here, so that's 8, then let's check what's actually going on around the vicinity of 8. So the cumulative distribution function, if I go from 0 up until 8, then if I include up to and equal to 8, this is 0.96917 and so on. Yep, that's fine. That's just under 5% leaving over though. So let's try for 7. So up to and including 7. So if we go up to 7 and including 7, then that is going to be 0.9117684. So Nazir claims he has a method to help him win more than 1/3 games. Test his claim 3 of them played the game. Stating hypothesis clearly, test. Okay, so it doesn't actually say which one. What we can do, actually, is we can just see where that 16 lies. Well, put it this way. Whether you want to argue whether it's 8 or 7, 16 is way out here. In actual fact, the probability that x is greater than or equal to 16, which is 1 minus the probability x is less than 16, which, by the way, probability x is greater than or equal to 16 is x is greater than 17, which is the same as 1 minus the probability x is less than or equal to 17. So if I want the cumulative distribution from a lower bound of 16 up to... Wait, what? Oh, I've still got it as 15, you silly boy. Oh, that's completely ruined it. Okay, hold on. That's where I went wrong. Binomial, inverse binomial, 0.95. Number of trials now is 32. Right, 15. So that is actually 15. Interesting. And so now if I go... that's not going to be a 7, is it? And these are going to be wrong. Sorry, I forgot to change the number of trials to 32. So if I go from 0 up until 15 for a 32 one, that is actually 0.9623. And if I go down one to 14, that's 0.92233 and so on. Clearly, the 16 is the other side of that. And if I actually calculate where the 16 and above lies, then the probability that x is greater than or equal to 16 is 0.03765 to 4 decimal places, 0.0377. This is clearly lower than the 5% level of significance. So you're actually in this H1 region. So stating your hypothesis clearly tests the claim at the 5% significance level, then the answer is yes. At the 5% significance level, there is evidence to reject H0 and supporting the claim that Nazir has increased his chances of winning. Done. In actual fact, 16 isn't going to be that far out, is it? It's going to be over here somewhere. Okay, so the probability of 16 or being 16 or greater is in the top 3.77% weirdest outcomes. Now that's clearly above the top 5% outcomes, so we'll accept it. So we'll accept that H1 is the better decision to have here, and I put H0 twice, you silly boy. That's H1. It's the null hypothesis, alternate hypothesis. Okay, fine. Only a few mistakes, but no, that's the right answer. Okay. So, past records show that 15... Well, actually, pause the video, give it a go yourself. Okay. Past records show that 15% of customers at a shop buy chocolate. The shopkeeper believes that moving the chocolate closer to the till will increase the proportion of customers buying chocolate. Okay, so we're already sniffing that the probability is 0.15, and the shopkeeper believes that if he does stuff to it, then it's going to increase by 0.15. So it's going to be greater than. After moving the chocolate close to the till, a random sample of 30 customers is taken, and 8 of them are found to have bought the chocolate. Julie carries out a hypothesis test at the 5% significance level to test the shopkeeper's belief. Julie's hypothesis is shown below. So H0, P equals 0.15, H1, P is greater than or equal to 0.15. First mistake, you can't have greater than or equal to 0.15 because then there's overlap between these two things. So if there's going to be an ask for a mistake, then it should have been H1 is that P is strictly greater than 0.15. So that's a potential mistake. Let X equal the number of customers who buy chocolate. Fair enough. Then X is distributed normally, binomially, with N is 30, yes, and probability of success 0.15. Okay, probability of x equaling to 8 is 0.0420. Okay, that's weird. What should they have wanted? Well, if they wanted to test against probability being greater than 0.15, then here's my distribution. They actually wanted the top end of the 5% most freakiest ones. So actually this is a mistake. The calculation they should have done is the probability that x is greater than equal to 8, which is 1 minus the probability that x is less than or equal to 7. And on our calculators, that's going to be 8 upper is 30. Probability num trials is 30, probability of success is 0.15, and that apparently is 0.06978, so I'll put 0.698, sorry. Okay, yep, so that's wrong. And then 0.0420 is less than 0.05, so reject H0. Well, that's a mistake carried forward as well. In actual fact, 0.0698 is greater than 0.05, so what would actually happen is you would accept H0, because the 6.98% line would be here, right? Because this region is 6.98%, so it would be sitting nicely in the H0 acceptance region. So if we were actually to carry this out, we would accept H0. So that mistake has actually completely changed the outcome. It's gone from rejecting H0 to accepting H0, i.e. there's not enough evidence to suggest that by moving the chocolate closer to the till that the proportion of customers buying chocolate increases. So anyway, there is sufficient evidence, so you'd actually say there's insufficient evidence to suggest, yeah, so we're accepting H0. Okay, identify the first two errors. Well, the first error was over here. It was with the hypothesis, and the second error is they should have used the cumulative distribution of the binomial to find probability of x being greater than or equal to 8. Okay, explain whether or not these errors will affect the conclusion of a hypothesis test. Give a reason for your answer. Well, yes, it will, because it's now in the acceptance region as opposed to the critical region, and it will completely change it from H1 going to H0. It completely changes the answer. Yeah, writing something like that would be the thing. Find, using a 5% level of significance, the critical region for a one-tailed test of the shopkeeper's belief, and the probability in the tail should be less than 0.05. Okay, so go to our calculator, distribution, binomial, inverse binomial. I want the upper end to be 5%. So it's saying my inverse binomial is 8. So x is greater than or equal to 8. But let's check what the probabilities are for x being greater than or equal to 8. No, 8 is the boundary, so we want, okay, we need to check x is greater than or equal to 9. What is that? Well, go back to my distribution. Cumulative distribution, let's have my lower at 8, upper at 30. Okay, so that was my, as I said, 0.0698. If I try it with 9 though, this time, so the probability that x is greater than or equal to 10, this is 0.0277. Have I done that right? No, what am I doing? What am I saying? That's for 8. That's for 8. This is for 9. Yeah, sorry. So I want my probability should be less than 0.05. Well, this one isn't. So the critical region isn't greater than or equal to 8. So the critical region is x is greater than or equal to 9. So if the shopkeeper had recorded 9 people, that would have been just enough to tip it in the other way. Find the actual level of significance of this test. Well, it was given here, it was this probability, which is 0.027, what was it? I need to calculate it again. 0.2777, so that's 0.0278 to 4 decimal places, which is 2.78%. It's 2 decimal places. So the actual significance level of the test is 2.78%. Yeah, that's it. Cool. Well, hope you enjoyed that. There's plenty of stuff to be getting through. And yeah, have fun.